Okay, now we have a more interesting problem here. Boundary conditions are more complicated. We have a pin here and a roller here, and we got a beam between these two connections, and let's say we have a load of value equal to 2k right here. Let's say from here to here is 1 meter, from here to here 5 meter, and what we want to do is to find the equation of elastic curve, and in particular the deflection at the middle of the beam right here, and also the slope at point A and B. Lots of things. So the deflection at the middle of the beam and the slopes at point A and B. Okay, so immediately before we start problem, let's say EI, we have a Young module of elasticity and I, and let's say they're constant across the beam, and we don't want to say E dot I is equal to 1. We can do that, but we want to keep the value. All right, so let's go ahead and draw the equation of elastic curve. If I draw the equation of elastic curve, I will get something similar to this. The maximum deflection is not necessary in the middle because the loading is not symmetric, you can see. So I get an equation of elastic line which looks like something like that. So you can immediately realize the slope, let's use green, at point A is not 0, unlike the wall. You see, if we fit a line to the curve, elastic curve at the A, we have some negative slope theta at A, and if we fit a line to point B, then we get theta B, which is positive. So now the question is, how can I apply boundary condition if I don't have a slope? Well, the answer is easy. I know that point A is a pin. That means if I apply any kind of loading, point A is not going to go up or down. So the vertical deflection of A is equal to 0. Similarly, see if I can have a bigger phone. Yeah, this is probably too big. Let's get something that is thinner. All right, V of A is 0, and also same thing, I know that this roller right here, as long as the loading is downward, it's not going to move. At point B is not going to move. If I have a upward loading, point B may go up and the system become unstable. That's what we discussed in a structural analysis class. But because the 2K force is down, point B is not going to move. Only point B. Everything on an elastic curve will move except point B and A. So the vertical deflection of point B also is same. Now if I take my X from the left and I cut this beam, like I always do, you could take it from right. So you can write this as V of A is equal to V, equation of elastic line, at X is equal to 0. So this is one boundary condition. The other boundary condition is V at X is equal to 6 is equal to 0. Right? So now I'm ready to solve this problem because I know that equation like this, second derivative of V with respect to X is equal to M over EI. This is a second order ordinary differential equation. So it would give me two constants of integration. So I need two boundary conditions, which I call them 1 and 2. Also, don't forget, when I write this equation from x is equal to 1 to 5, and then from 5 to 6, then I get two v1 and v2. And then I'm going to need two more constant of integration, which I use the continuity of slope and the continuity of elastic curve at point 5 to satisfy those conditions. So let's go ahead and do it. This equation, I'm going to define v1, which is valid between v1 x 0 and 5, and then I'll also define v2, which is valid between 5 and x between 5 and 6, right? So for each one of these, I have two equations. Second derivative of v1 with respect to x2 is equal to m over ei, and the second derivative of v2 is equal to m over ei. In fact, v1 and v2 are the same thing, because we have a 2k in the middle, which causes discontinuity to separate physics. We had to create it, two functions, v1 and v2, but in fact they're just expressing the same nature. This equation, second derivative is equal to m over ei. Now let's go ahead and add boundary conditions here. I know that v1 at x is equal to 0 and v2 at x is equal to, so I'm adding equation 1 and 6. v2 at x is equal to 6 is equal to 0. So here immediately let's use a different color. From this equation I get two constant of integration, c1, c2. From this equation I get two more, c3, c4. How many conditions do I have? 1, 2. So I need two extra conditions. And what are those two extra conditions? Based on what we discussed previously, hopefully yes, I can zoom in this software. Look at this point. If you fit a line to the elastic curve, you see that first of all v1 is before that, v2 is just after that, because the equation of elastic curve is continuous. That means beam is not going to break. v1 at x is equal to 5 is equal to v2 x is equal to 5. That condition is called continuity of elastic curve, because the beam is not going to break, it's continuous, right? Similarly, the derivative v dot, instead of dv dx, I could simply call it v dot, at x is equal to 5 for v1 is equal to v2 dot x is equal to 5. So these are additional two equations that I need to apply to get four constant of integration. So let's put them right here. d v1 dx, or v dot 1 at x is equal to 5 is equal to v dot 2 at x is equal to 5, and also v1 at x is equal to 5 is equal to v2 x is equal to 5. So at this point 5, where I have the 2k force applied, I have the left here is equal to the right, the elastic curve, and also the derivative also should be same, continuous. So now I need to use a different color. If you look at inside this enclosed area, I have what mathematicians call it a well-posed problem. That means I have enough equation and enough conditions to get a unique solution, right? So here I have four constants of integration and I have four additional conditions to satisfy get all constant of integration, and then I'm ready to get the equation of elastic curve for V1 and V2, right? So let's go ahead and solve this equation first. Let's call this equation 3 and call this equation 4. I don't know how this little line right here came to existence. Yeah, it was a glitch. 3 and 4. So I'm gonna solve equation number 3. But before I solve equation number 3, I need to have the reactions at A and B. So let's do that. Before I solve equation number 3, let's do the FVD exactly the way we did in vector statics, and this problem is statically determinate, so it's easy. So I have a 2k right here. From here to here is 1, from here to here is 5. It goes by and ay right here. Ay, by, 2k, distances are given. So I can immediately say ay, negative 2k plus by is equal to 0. And moment about A gives me 2k times 5 negative plus by times 6 positive is equal to 0. Solving that give me by is equal to 10k over 6, and let me bring my calculator, and then I plug to get ay. So let me bring my calculator. Calculator. All right. This is going to be 1.67k, and when I put it there to get ay, negative 2k plus 1.67k is equal to 0, then I get, well, I should have used 4 significant digits to get 3 accurate significant digits, but this is just a demonstration. Let's take it to the right. 2 minus 1.65, obviously it'll get ay is equal to 0.33k. So my beam is like, put it here. So instead of ay, I can just simply put 3k. Don't forget that k. Instead of by, I just put 1.67k and 2k and everything. So here I don't need this information. Let's open up some space. Basic equations of vector statics. Alright, so now I'm ready to go ahead and cut this system and find the moment diagram, because then I want to plug it right here in equation number 3 and 4, and then double integrate, apply all those boundary conditions, and do the algebra and get the final elastic curve, equation of elastic curve. So if I do that, let's take your x from left and cut it somewhere here. So your FVD will look like 0.33k right here, mx, vx, and nothing else. And from here to here is also x. So if you write moment equation about point x, you get mx positive, Vx doesn't have any contribution to the moment, and negative 3k times x is equal to 0. So the moment is equal to 0.33k x. Alright, so now I found why I didn't use black here. I should have used black. I found the moment for which satisfies the range between x 0 to 5. So that means the moment right here, this moment is equal to 3k, let's zoom here, 0.33k times x. Okay, now I want to find the moment in equation number 4 right here for the second part. Well, if I do that, I can either take the right or take the left. Okay, I take the one on the left. So I continue cutting. Need another color here. I continue this x. Then I cut it somewhere here. So my FED will look like here 2k. Now we need black. Point 3k. From here to here is 5. From here to here is x, and then you have mx and vx going down. If you put it on the right, mx is up, vx is also up on the right side. On the left side is down. So that's pretty much all of it, what you have in your FED. Then you write the same equation. Let's clean up some space here. If you write equation of moment about point x equal to 0 and expand it, then you get mx positive plus 2k times x minus 5 negative 0.33k times x is equal to 0. That means you have mx plus 2k minus, put in calculator, 2 minus 0.2 minus 0.33, 1.67 k, don't forget the k, x, negative 10k is equal to 0. Take it to the right, so you get mx is equal to negative 1.67 k x plus 10k. So let's put x in this equation. Let's put x is equal to 6. See what we can get. It should be 0 because the point x is equal to 6 is a roller, so the moment should be 0. Negative 1.67 times 6 is equal to 10. Yeah. So yes, that's your moment diagram or equation, and this equation corresponds to this one. I just simply write it there. This is simply m is equal to negative 1.67k times x plus 10k. So I'm just ready to go ahead, and I wish I could zoom like this. Yeah, I'm just ready to go ahead and do this integration, equation 3 and equation 4. Let's start with equation 3. If I integrate it once, then I get EI dv1 dx is equal to 0.33 k x2 over 2 plus c1. This is integration of equation number 3. I brought ei to the left, integrate, so the second derivative becomes first derivative on the left side, and then just integrate m, which is 0.33 k x squared over 2 plus c1. Okay, well, do I have a boundary condition that I can apply right here to get c1? Then I'll take a look at my list. This is the list of information I have here. I have v1 at x0 is equal to 0. That doesn't help because right now I have the derivative. And then I have this little equation right here, which I mark it with the solid rectangle. But this equation at this point is not going to give me exact value for c1 because the right side, this equation is kind of like implicit. It's not a known number on the right side. The number on the right is just a function of v2. So at this point, I'm not going to apply any condition because I don't have it to get c1. So I go ahead and take one more integral to get ei. So if you integrate both sides, then you get ei v1. Okay, I need to rush because it's 15% of my iPad, and hopefully I have enough power to finish up this problem. ei v1 of x is equal to 0.33 k, so that's going to be x3 over 6 plus c1x plus c2. This is a full integration which gives me equation of elastic line for region between 0 and 5. But still, I have two unknowns that I need to work on, c1 and c2. Don't forget that. Now let's go to equation number 4 right here and integrate that equation. So I have, if I integrate that once, I get dv2 dx is equal to, also I have ei here, ei dv2 dx is equal to integral of the moment relation, which is 1.67 k x squared over 2 plus 10k x plus c1. I take one more integral, ei v2 is equal to negative 1.667 k x3 over 6 plus 10k x2 over 2 plus c1. Well, in fact, this info we already have c1, c2. This is going to be c2. Sorry, c3, because we already have c1 and c2. So I have to introduce more unknowns, more variables. So this is c3. Therefore, when I integrate that, it's going to be c3 x c3 x plus c4. So I took one more integral of that to get ei v2 is equal to negative 1.67 k x3 over 6 plus 10k x2 over 2 plus c3x plus c4 right here. Now I can apply my condition to get 4 constant. You see c1, c2, let's circle that, c3, c4, 4 constant, 4 condition. What are the conditions? The first condition say v1 at x0 is equal to 0. So let's write it here. ei v1 at x is equal to 0 is equal to 0. That means put 0 in this equation. Then you get c2 is equal to 0 immediately. Okay, because v1 at x is equal to 0 is 0. Now let's apply this condition right here. v2 at x equal to 6 is equal to 0. So in this equation, let's say put v2 is equal to 0. So here I have ei v2 put x is equal to 6 is equal to 0. So this is going to give you negative 1.67 k 6 to the third power over 6 plus 5k, 10 over 2, 5k, then 6 to the second power is 36, okay, plus C3 times 6 plus C4 is equal to 0. Alright, if you do this simplification, if you simplify this number, put it in a calculator, then your equation become 6C3 plus C4 is equal to, put it in a calculator, so you get 36, 6 to the 3 divided by 6 is 6 to 2, 36. So in fact you get 36 times 5 minus 1.67. 1.67. So 5 minus 1.67 inside parentheses times 36. And then you take it to the right. So 6 C3 plus C4 is equal to negative, don't forget the K, 119.88 K. So 6 C3 plus C4 is equal to negative 119.88. You can round it up to negative 120 K. So this is one equation you have. So far, let's make these, highlight them. Where is my highlighter? Here. And I need traditional yellow for highlighter. This is one useful thing. This is the second useful equation. So I apply two conditions. V at x0 is equal to 0. V2 at x6 is equal to 0. Now I need to apply two more to get all the conditions that I need. So the first equation that I'm going to apply right here is the derivative of v1 at x. I'm working on this equation. The derivative of v1 with respect to x at x5 is equal to the derivative of v2 with respect to x at x is equal to 5. All right, so let's take a derivative of this. So you get ei dv dx is equal to 0.33 k. Then 3 with 6 become 2. Then you get x2 over 2. Because if you take integral, it become x3 over 6, right? Plus c1. c2 completely vanishes. Okay, so this is this derivative evaluated at x5 according to this relation. You see x5, that means this relation evaluated at x5 should be equal to the second one evaluated at x5. Where is the second one? Right here. Solid rectangle. I showed you the solid rectangle. So if you take derivative of that equation, then you get ei dv2 dx, which is equal to negative 1.67 k x2 over 2 plus this is going to give you 10k x plus c3, and c4 vanishes, is constant, right? So you get c3. So this also should be evaluated at x5. That means this equation should be evaluated at x5. Now let's go ahead and put the numbers in. So the first equation, if you put 5, then you get 0.33 .33 times 25 divided by 2, which is 4.12 K plus C1 is equal to the second equation, put 5 in it. Then you get negative 1.67 times 25 divided by 2 plus 10 times 5 is equal to 29.13 okay, K plus C3. That's it. This is another useful equation that we need to solve. So let's use highlighter. There you go. Okay, so as you can see here, I got a relation that the first one right here, C2, this is the easiest equation because C2 is 0. They're not coupled. But the other equation, C3 and C4 are showing up in this equation, and then C3 and C1 are showing up in other equation. So these are coupled equation. So let's go ahead and apply the last condition. The last condition says V1 at x5 is equal to V2 at x5. If you multiply by EI both sides, that means EI V1 x5 is equal to EI V2 x5. What is EI V1? Right here. This equation evaluated at x5 should be the other one evaluated at x2. So I go ahead and apply here 0.33k over 6. Put 5 here, 5 to the third power plus C1 times 5 plus C2. This is equal to negative 1.67k, negative 1.67k, 5 third power over 6 plus 5k over times 25, 5 to the second power, which is 25, plus C3 times 5 plus C4. So this is the last equation, which actually has all the unknowns in it. It's very coupled equation. So here I know that, well, what is my C2 right here? C2 is 0. So this equation C2 is 0 here, right? So I'm just ready to simplify this equation. Let's go ahead and put in calculator. So I have C 5C1, this equation 5C1, negative 5C3, negative C4, I'm bringing the one on the right, is equal to negative 1.67 times 5 to the third power divided by 6 plus 5 times 25 plus 5 times 25. My calculator is not collaborating. Okay, negative 0.33 times 5 to the third power divided by 6. So this is going to be 83.3. Okay. This is the last equation. So what I did, I just kept this 5C1 on the left and C2 is 0. And also I brought negative 5C3 to the left, negative C4. So all I did, I subtracted this one on the right by this one on the left. So let's double check the result one more time. Negative 1.67 times 5 3 divided by 6 plus 5 times 25 negative 0.66 divided by 5 to the 3. Yeah. So this is the last equation that I obtain. Don't forget that there are easier way to solve this problem. I will show you the Heaviside function if you find the opportunity. But this is called the direct method. That means you write all the equations, you apply all the boundary condition, and then you solve the equation, all these constant, for constant integration simultaneously. All right, so let's write down the final equation for C1, C2, C3, C4. Well, I know that C2 is 0. So my constant are C1, C3, and C4. 3 equations here. 1, 2, 3. And 3 unknown. So I have one equation that I can write here. Equation number 1, 6C 3 plus C4 is equal to negative 120. Let's round up that number to negative 120 K. This is one equation. Equation number 2 is equal to C1. Let's bring all the constant to the left. C1 minus C3 is equal to, I'm just working on this equation number 2 right here. You see, I bring all the variables to the left, constant to the right. C1 minus C3 is equal to 29.13 K minus 4.12 is 25 K rounded to 25 is the second equation, and the third equation is 5C1 minus 5C3 minus C4 is equal to 83.3 K. So 5C1 minus 5C3 minus C4 is 83.3 K. So this equation, these are 3 coupled linear equation. 3 equation, 3 unknown. How do you solve it? Well, you try to eliminate one, put it in the other, and then you get 2 equation, 2 unknown. How do you solve it? Then you try to eliminate one and put it in the other. You get 1 equation, 1 unknown, and then you substitute backward. This is called Gaussian elimination. Another method in the exam or test, you can just put it in the calculator. Right? Lots of calculators, they have linear algebraic equation solver. You can put up to like 15 equations. Another method is to use online calculator. You can ask, well, I have this system of equation, I want to solve it. And then you just put the constant here, coefficients here, and then they're going to solve it for you. So I'm going to, usually the easiest way to do that is just simply to eliminate one equation. For example, I know that, well, if I multiply this equation by 5, let's do that. So you get 5C1, multiply this equation that I'm check marking right here by 5, both sides. So you get 5C1 minus 5C3 is equal to 5 times 25, 125. But always put it in calculator. 5 times 25, 125K. And then look at here. 5C1 minus 5C3 is 125K. Isn't this value here? 5C1 minus 5C3. So instead of that, I can just plug in 125K, and then I have negative C4 is equal to 83.3K. Then you can find C4 immediately. That greatly simplifies your job. So C4 is equal to 125 minus 83.3K. So C4 is equal to 41.7K. Don't forget that K. And C2 was already 0. So far we obtained 2. Okay. I'm going to substitute back here in equation, this equation with a star. You see this equation to get C3. So 6 C3 is equal to negative 120K negative C4. Negative C4 is 41.7K. This is going to be 160 negative 161.7K. 20, 40, negative 161.7K. Then divided by 3, you get divided by 6, you get C3 is equal to negative 20, let's see, 120, 41.7 divided by 6, yeah, negative 26.95, let's say negative 27K. So all I need to is to find C1, right? I have obtained, let's write here, C3 is equal to negative 27K. So the last thing is C1. Which equation do I need to use C1? This equation is the easier one. So you say C1 is equal to 25K plus C3 is equal to 25K plus C3 is equal to negative 27K. So you get negative 2K. So C1 is equal to negative 2K. So then you have complete description of the elastic curve. Let's write it here. Your elastic curve versus any x is equal to 2 equation. When your x is between 0 and 5, and then when your x is between 5 and 6. The first equation, which one was it? Right here. Do you see that? So it's 1 over EI. I wish I could copy this section. Yeah, I think I can copy this section. Can I copy it? Can I move it? Yeah, I can move it. Move it. Go down. How can I go down? Come on, please. Oh, I should do that. Yeah. So many writings. Yeah, the first equation is that, which here C1, right now we already have the value. C1 is 2K right here. C2 is equal to 0. What about x between 5 and 6? If I come here, then I realize that the second one, this copy thing is so useful. The second one is right here. So I just use my copy technology. There you go. And then I simply just move it. Drag it all the way down. Sometimes we write a lot of equations, but there you go. Don't forget, when you say v of x, then right here, when you say v of x, that means that if you solve that for v of x, that means this right hand side divided by 1 over ei. Similarly, this one divided by ei. And then you can eliminate this part right here. Similarly, here. There you go. And what is C3 and C4? C3 and C4 is negative, where is C3 negative 27K, so C3 is negative 27K, and C4 is 41.7K. So you have a complete equation of elastic curve. Look at the elastic curve. What is the order of your elastic curve? Right here, highlighter, is the third order. You see that? So your equation is a third order polynomial, the equation of elastic curve. And when you plot it, I recommend you, if you go ahead and plot it, you realize that it looks like something like this red line. So this is a use a red line here. So this red line right here is a third order polynomial that we obtained it completely between here and here and between here and here. As you can see, this is the piecewise. They call this kind of function that you have a bracket and two different descriptions. They call this piecewise continuous, this kind of functions. All right, so if you want to find the deflection at 5, what do you do at this middle? Back to the main objective. Well, you just come here and see where is that 5 located in. You say, well, the deflection at x5, then you say, well, I should go to this equation right here, right? In the middle. Or, sorry, the middle, here the middle is not 5. The middle is from here to here is equal to the entire length, which is 6 divided by 2 is 3. So if you want to find the deflection in the middle, you should say x at 3, not 5. So which equation should I use? The top or bottom? Well, the top, right? So you put x3 here, and it gives you exact deflection, just a number, and in the middle. What about the slope at A, point A? How do you find the slope at point A? Right here. Well, you come here, take derivative of the first equation, because this is in the range. Point A is right here, right? So you take derivative of this equation, d dx, that's your slope, or v, or theta, sorry. And you evaluate it at point 0, okay? Then you get your slope at point 0. What about the slope at the end? Well, you take the derivative of this equation and you evaluate it at x is equal to 6. Don't forget, don't put x0 here, because x at the end is 6, okay? So this is all. If your problem, as you can see, when you don't have simplicity of wall, then you should have more equations, and you have to solve more simultaneous equations. And this is a problem with the direct method, and the work around it is a method called Heaviside function that we teach in the, hopefully I'll teach a little bit in this class, but we extensively teach in structural analysis. So you can, the interesting thing is, you can solve this entire problem with just one line, right? And still you have two constants of integration. So you can solve this entire problem with just one line. Hopefully, when I cover the Heaviside function, I'll come back to this problem and solve the exact problem using Heaviside function. And you see, we get exactly the same final result, but with the one line approach. This final result right here. This final result right here. Okay, that's enough for the third part of the lecture, and I'll see you later.